Now, let us give a necessary and sufficient condition for uniform convergence of a series. So, which is called as Cauchy criteria for uniform convergence of a series of function. So, let us write it as a theorem. So, which is Cauchy criteria for uniform convergence. So, this theorem states that a series of functions defined on an interval closed interval AB converges uniformly on the same interval AB if and only if for every epsilon greater than 0, for every epsilon greater than 0 and all x belongs to the interval and x belongs to the interval AB. So, there exists a natural number n. So, there exists a natural number n such that this mod of f of n plus 1 of x plus f of n plus 2 of x up to f of n plus p of x is less than epsilon for all natural number n, greater than equal to the particular number n and p greater than equal to 1. The proof of this theorem is as follows. Proof. So, consider the sequence of functions. S n x such that the function S n x is defined as f1x, f2x up to fn x. So, now we already know about the Cauchy criteria for uniform convergence of a sequence of functions. So, therefore, from this theorem, so now from Cauchy criteria of uniform convergence of a sequence of functions. So from this theorem, we have this sequence Snx, this sequence of function Snx converges uniformly, if and only if for every epsilon greater than 0 and for all x belongs to the interval AB, there exists an integer such that n such that this mod of Sn plus p of x minus Snx is less than epsilon for all natural number n greater than equal to the integer n and p greater than equal to 1. So this Sn plus p can be written as f1x, f2x up to fnx, fn plus 1x up to fn plus p of x, and this Snx can be written as f1x, f2x up to fnx. So this is less than epsilon for all natural number n greater than equal to the integer n and p is greater than equal to 1. So as a result, we will get f of n plus 1 of x, f of n plus 2 of x up to f of n plus p of x, which is less than epsilon for all natural number n greater than equal to the integer n and p greater than equal to 1. So hence this theorem is proved. We conclude this module with the following application of Cauchy criteria for uniform convergence. So let us consider this problem. So consider the series of functions this series is given by sum x by 1 plus n square into x square. Let epsilon be any arbitrary positive number. So epsilon greater than 0 be arbitrary and this x is strictly greater than 0. Then we have fmx plus fm plus 1x up to fnx. So this can be written as, so fmx is nothing but the function x by 1 plus m square into x square. So similarly fm plus 1 is the function x by 1 plus m plus 1 whole square x square up to this fnx is the function x by 1 plus n square into x square. Since the number n is strictly greater than m, so we have 1 plus n square into x square will also strictly greater than 1 plus m square into x square. So, as a result we will get 1 by 1 plus m square into x square is strictly greater than 1 by 1 plus n square into x square. So, which implies that, so x by 1 plus m square into x square is strictly greater than x by 1 plus n square into x square. So, give it a equation number 1. Similarly, we can get, so x by 1 plus m plus 1 whole square into x square is strictly greater than x by 1 plus n square into x square. Give it another equation number. So, similarly, we will get x by 1 plus m plus 2 whole square into x square is strictly greater than x by 1 plus n square into x square. Give it another equation number, and proceeding this way, finally we will get x by 1 plus n square x square is equal to x by 1 plus n square into x square. So, give it also equation number, suppose star. So, now if we add all the inequalities in the equation number, then we will get, so adding all the inequalities with the equation numbers, we will get left hand side of the inequality as x by 1 plus m square into x square plus x by 1 plus m plus 1 whole square into x square up to the last term will be x by 1 plus n square into x square, and which are strictly greater than x by 1 plus n square x square up to x by 1 plus n square x square. So, since we have added n minus m plus 1 terms in the right hand side, so therefore, this sum will be equal to, so this is equal to n minus m plus 1 into x by 1 plus n square into x square. So, note that the left hand side of the inequality is nothing but f the function fmx plus the function fm plus 1 x up to f n x, and sum of these functions is strictly greater than n minus m plus 1 into x by 1 plus n square into x square. Now, if the given series of function is convergent, then we can apply Cauchy criteria of convergence. So, now if this series x by 1 plus n square into x square is convergent, then by Cauchy criteria of uniform convergence So we have for every epsilon greater than 0, so there exists a natural number n. So there exists a natural number n such that what we have, so mod of fmx plus fm plus 1x up to fnx. So this is strictly less than epsilon. So whenever for x is strictly greater than 0 and n comma m greater than equal to the number n. So now from the previous inequality we already know that this sum f mx fm plus 1x up to fnx is strictly greater than n minus m plus 1 into x by 1 plus n square x square. So therefore using that previous inequality we will get this one as n minus m plus 1 into x 1 plus n square into x square is strictly less than epsilon for x greater than 0 and the number n and m strictly greater than equal n. So now consider n and m such that this n minus m plus 1 is nothing but the particular natural number n, and we assume x is equal to 1 by n. So since x is strictly greater than 0 we can assume this. So then from the inequality, that is from the last inequality, what we get? So in terms of, so from this inequality n minus m plus 1 into x by 1 plus n square x square less than epsilon, from this inequality, so instead of n minus m plus 1 we will put capital N, and instead of x we will put 1 by n, and in the denominator we will get 1 plus small n square, and instead of x square we will get 1 by capital N square, and which is less than epsilon. So as a result we will get this as, so n square capital N square by capital N square into small n square, and which is less than epsilon. Alright. So since small n is greater than equal to capital N, so therefore, so small n square is greater than equal to capital N square. So therefore from here we will get, so n square by n square n square. So this is less than equal to n square by n square into small n square. We have this is less than epsilon. So from here we will get capital N square by 2n square is strictly less than epsilon. So from here we will get epsilon greater than 1 by 2. So since we have assumed epsilon to be any arbitrary positive number, but in this case we got epsilon to be greater than 1 by 2. So hence we have arrived at a contradiction, so which is a contradiction as epsilon greater than 0 is arbitrary. So, therefore, the given series is not uniformly convergent. Therefore, the series summation x by 1 plus n square into x square is not uniformly convergent. Dear learners, that's all for today's module. Thank you.